Hello everyone. In this video I'm going to just briefly show you the idea behind the numeric integration. I know you have learned the calculus about the analytical integration, but for some of the functions you are given, you are not able to derive it analytically. So in some of the case, most of the engineering problems, sometimes you need to use the numerical integrations. So understanding the integration, first of all, if you want to, for example, integration on the area given by a curve. So for example, you want to find the area behind or beneath this curve. How are you going to do that? Okay, so analytically, just doing the integrations against that function fx, which you can see right, we can do that integration area equal to fab fx dx. However, in most of the case, the curves may be very complicated. So you end up, you wanted to discretize the function into some little, cylinders like this, or little bars, just to approximate the area like that. So a continuous a curve like that. Now you need using multiple bars just to approximate the total area. You're adding all of them together, you get the total area of the integrations. So now let's go into a simple rule. There are many ways to calculate that areas. Okay, a simple rule is so-called midpoint rule. Okay, what that means is, if you look at that figure here, let me copy over this. Okay, we can just simply copy that figures as an idea, right? So make it larger so we can see the things clearly. So midpoint rule basically means for each of these bars, okay, you just using the the middle point of each bar. For instance here, x1 for the first bar, x5 for the fifth bar, and x9 for the ninth bars. And then you use that middle point value x1 times the height, okay, the height of these bars. Essentially, if you know the function f, okay, fx1, this will give you the area for that little bar, and when you're adding them up, you will get the final answers, right? So what I mean here, okay, x1, if you know the x1, you substitute that to the function, you will get the height, which is, for this case, give you fx1. And the distance for this bar is normally is a given interval, let's say delta x. So for the little area, the first bar area is now equal to delta x times fx1 in this case. Okay, and what if we want to add all of them together? So essentially that is giving us the total integral is approximate to how many of these. Let's add them up. Okay, delta x is always equal for them, so I take it out, and then I adding up fx1, the first bar, and following that x2, and you can go to fxn. So n n is the total interval you defined. So for example, here is 9, n in this case is 9 for these approximations. Now, let's say how we're going to simplify these equations. First of all, is delta x can be equal to what? You know the boundary from A to B, and you know the total interval n is 9. So let's do that. So B minus A is the total distance, right, between A and B, and divide by the total interval. Let's say n is the number n. Sometimes using the capital N is denote the total number, and the small n is denotes the value you are now calculating. Okay, so delta x is defined by these equations. Now you want to know how to find this middle point value, for example x1. So let's put a slash or a top line above the x1, or you can say x2, or this value. Let's call it, this is the middle point value, right? So once you think about each of the middle points, let's just write it. So xn should equal to half of xn minus 1, the lower bound, to the upper bound, right? So if I give you an example how to calculate x1 in this case, you need to think about x1 essentially is half of the bar here. Let's say this point is x0. Let's make it longer, x0. And this one should be x1, right? So in reality, there should be a bar above all of this value here. So here is the average value we want to use. So essentially, x1 bar is equal to x0 plus x1 in this case. So this function can be even simplified by the equation I'm given here. So the detail of these derivations I have already given here, so I'm not going to cover in this video. So you can go through here. This is the derivations to basically showing the average value here is given by this equation, right? So once you now know this xn, now let's substitute that to the above equation here. So again, let's write this integral. Now is equal to what? Delta x is replaced by that function b minus n divided by capital N, and we use this sigma, and essentially is the sum up function. To sum up all this value here, we can just simply use f x n bar. So this is essentially the equivalent function to this one. So how to code it? So basically, now we want to write a code to implement that calculations. So the first of all, the step I will do is to import a mass function, and then we define some parameters here. N is being this total interval. It's the number of intervals in this numeric integration. You can define any number here, but the higher the better, basically. The higher means that you have more interval, then you will be likely to approximate this area more accurately. And A is the lower bound, and B is the upper bound, right? So once we define the parameters, now move to create a functions in Python to implement the function just to implement this part. So here I define equation here. Let's type it in font view so you can understand what I mean here. Define, integrate. Okay, this is your function. Now you give 3 parameters n, a, and b. Okay, and you want to actually define a sub-function which is your fx. Let's say define fx here. And now let's say f is equal to your given function. For this case, we just use a simple linear function as shown here, fx equal to x. This is your function you want to integrate and return f. Okay, so this essentially return the value of what you type here. Done for this part. Now we need to define a initial value. Let's say value equal to 0, and we define a total area, which is essentially the final value we want to calculate. Give an initial value at the beginning. Okay. Now we want to implement this part, the function here. So essentially we want to do a for loop to adding up all the small areas together. So for loop, and for n is essentially the iteration number n in range from what? From 1, number value 1 to n plus 1. And okay, so we can so we resume the calculation here. Essentially what the for loop we wanted to do, okay, we should start from a range from 1 to n. You want to implement from the number 1 to n. The reason we use n plus 1 because the range function normally only give you the, if you give a n, you end up the maximum value is n minus 1. So this, in this case, we ensure we iterate from 1 to n. Okay, and then we want to know what is this x bar, how to calculate this value x bar. Okay, because that will be need to pass to our function. X bar essentially we have defined here is a plus 2n minus 1. Make sure you have a 2 times n minus 1 divided by 2 times n, and this part, and times b minus a. So this gives you the x bar. Essentially implement this function. Now you want to do a loop so that essentially it's adding up the value from the first, from the fx1, because remember we have the, if you expand that equation, so this function will end up have, okay, so essentially we want to calculate these parts. We want to adding each of them together. So essentially our for loop is iterated these values. Okay, let's just type now. Just think about the first value, how we're going to type the first value. Essentially is we pass the x bar to our function, and because each time the n is changing, so it will start from x1 bar until it go to xn bar. So when we use this function, essentially adding them up, right? Sum up all the values. Once you've done that, the total area essentially is the value we used here we're adding all of them together. Now we can divide or times the front part, which is delta x. Essentially is value times, you can write b minus a and divide by n. Okay, then this is delta x. Once you have done that, then that's finished. Then you need to return this total area as your integration functions. Okay, so that's done. Okay, so to check whether this is right, okay, I just put a integration node, just differentiate with my other function. Okay, it's running, and you want to call this function to evaluate this integral. So how we going to do it? Essentially, let's just use this function here. Okay, here is your answer using midpoint rule, and let's say we have just written another function in front of you that's integrate node, and let's just run it. Okay, n is not defined because we need to run this one first. Okay, n is round and this one is round, and we go back to here. Okay, this gives us the value 50, exactly same as the other function, the example function. So you can evaluate essentially, if you think about, okay, there's some issue in my one notebook. Okay, if you think about this is a linear function y equal to x, and I give you the value from a equal to 0, 0, and b equal to 10, I think. So I'm asking you the value of this area. So you know y equal to x, so this value should be equal to 10, exactly the same. And half of this volume, the area, so that area should be equal to 50. Okay, that's exactly the same as the calculation here you have done. Right, so that's give you a brief introduction of that, and I hope you can follow the following things to calculate the absolute and relative error, just to see if you change the integration number n from, for example, 2 to 20 or 200, what the difference you get. Okay, and also, for example, if you have a function different with this y equal to x, you can simply change your function here, you define here, from x to sin x, or all kinds of function, very complicated function here. You don't need to change the calculation here. Essentially the same in this part. Okay, so I hope this gives you a brief overview of these numeric integrations. There are other things like not midpoint rules. There's many other rules like Simpson rules, trapezium rules. So you can try to use the other method to see how you understand using numeric integrations. All right, thank you.